All right, time for a new unit. You're in Algebra 2, Module 1. We are now going to Unit 3 and the first lesson, simplifying rational expressions, but we're going to deal with rational expressions and radicals in this chapter. So we're going to really delve into that stuff. All right, moving on. So the first thing we want to take a look at here is what I'm dealing with this is we want to just go back to 5th grade, 4th grade, and all that. We're talking about fractions and equivalent fractions. So we're going to write two equivalent fractions to this one right here. Of course, this one right here is the fraction 1/3. Okay? Well, I want to get two other equivalent fractions. So I'm going to make another one here. I'm going to put a line right down the middle right here. And if I do that, how many parts are shaded? Because in the first part right here, it was 1 part shaded out of 3. And now I've got 1, 2 shaded out of 6. So that was an equivalent fraction, still the same size. And if we want to make even another one, I could do that. We could go and bust it up like this. And now I have 3 parts shaded out of 9. Well, these are all called equivalent fractions, okay? They would be equal to each other. The general rule we talk about here is if you got an A and a B and an N are all integers, where N cannot equal 0, because it cannot be 0 in the bottom denominator. We've always told that. You can't divide by 0. And also B is in the bottom here, so that cannot be divided by 0. So as long as N and B are not zeros, okay, if you have this thing on the top and this time on the bottom, N times each, you will get that, or you take it out, you will get that. So if I take it this one, 16/20 equal 4/5. Well, let's write this out here a little bit. Isn't 16 equal to 4 times 4? And that's over 20 is 4 times 5, isn't it? And that we're claiming it's equal to 4/5. Well, if I take a look at my piece right here, this right here is my N. That's what I'm pulling out. And if I divide that by that, those two pieces, don't I get 4/5 equals 4/5? The exact same thing. So those are equivalent fractions. Keep in mind, you could also always do what we used to do, which is cross products here. So if I do 16 times that, that's 80. And if I do 4 times 20, that's 80. And obviously 80 equals 80, so they are equivalent. Okay, that's the big key. All right, moving on. All right, so we're going to go back here and remember what from 9th grade and other years, which of the following are basically rational numbers, okay? And rational numbers, once again, can be written, any number can be written in a fraction form, okay? And another shortcut we always said is if you punched it in the calculator, you want to make sure it either repeats or it terminates. If it seems to go off your calculator without repeating, that's not rational. That's going to be hitting into the irrational case. So let's see what we've got here on these, okay? So, we'll take a look at the first one here. And I've got the fraction right here is 3/4. That, of course, is 0.75. So I'm going to circle it. That's rational. A lot of you guys say, oh, 3.14, that's pi. That's not rational. Well, yes, it is rational because 3.14 is a decimal. If I put it in my calculator, if I punch in 3.14 and I hit math, enter, enter. So remember that one. Math, enter, enter. So the enter, enter button. Okay, that changes any decimal into a fraction. If you can do it, you got a rational, okay? Pi is the first one that we know is not rational. That's 3.14156, blah, 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 going on and on and on and on. So it doesn't work, okay? So, not. 5 divided by 0 right here. Can we divide by 0? No, that's undefined. We don't know how to divide by 0. So that's not going to be rational. Negative square root of 17. Punch it in your calculator. You're going to get a 4 point whatever it is going on and on and on. That's not rational. Okay? Obviously, if I go back here, 23 is a number that ends. That's rational. Okay? I can put it as 23 over 1 also. 1 plus 5 square root of 2, 1 plus the square root of 5, right there, and there's no square root of 5 on the bottom to cancel it. This is going to be irrational, okay? Not going to be a normal number. -1 is rational. Okay, it ends. The next one, 6.022 times 10 to the 23rd. Okay, that just means move the decimal 23 spots to the right. It will turn and it will end. So that is rational. And of course, the number 0. What about the number 0? Well, it's a whole number in that. So we consider that in there as a rational. You can put it 0 over 1 and you've got 0. So the ones I circled are rational. The others are not. Moving on down below here, we want to determine some of these rationals and where they have exclusions and stuff. Well, I obviously have a rational number here with 31 over 47, and we don't have to worry about anything. The big thing is you've got to make sure the bottom doesn't equal 0. Well, I've got a solid number there, so like I said, the denominator is never 0, so this will always be a rational number. There's no restrictions, so no restrictions on this one. All right, the next one, we do have a little bit of an issue. I take a look at the bottom here. So I got 3a minus 2b. All right, I don't care what a and b are except for the fact that 3a can't equal 3b or 2b. If 3a, let's say, turned out to be 4 and 2b was 4, you would get 4 minus 4, which is 0, so it can't have a 0 in the bottom. So anything else is fine. As long as 3a minus is not equal to 2b, we're okay. So we got a limited restriction there on the bottom. Okay, we're going to move on. Okay, so if I take a look at my next example here, 3x squared plus 4, you're looking like, wow, what could make that equal to 0? Well, stop for a moment. You're not sure. When you're not sure, you set the bottom, the denominator, equal to 0. And if I do that, I bring the 4 over, I get 3x squared equals -4, okay? Divide by 3. So now I get x squared equals a -4/3. And of course, we know from the past, undoing the square, we square root, plus or minus. And can we take the square root of a negative number? No, so there's no real roots. So therefore, this parabola would never come down and hit the x-axis, and we don't get any roots out of it. And so in that case, I have nothing that's going to prevent it from it, and I'm not actually going to come up with anything, but there's no exclusions. There's no number you can think of to put in for x here that would make that bottom 0. Because if you put a negative number in, you square it, it becomes positive. You put a positive in, you square it, it's still going to be positive. So there are no exclusions here. So this denominator is never equal to 0. Okay, that works. The last one I want to take a look at here is this one. And I've got b squared minus 7. So I take b squared minus 7. And I set it equal to 0. Which means when I bring the 7 on the other side, I get b squared equals positive 7. And then I take the square root. And of course, we're taking square root as plus or minus. So b is equal to positive square root of 7. Or b could be negative square root of 7. So I have exclusions there. If I had a positive square root of 7 and I plugged it in, just to point out here, I would have 3 over, and the square root of 7 being squared minus 7. So that would be 3 over, well, the square root of 7 being squared is 7. And 7 minus 7, of course, is 0. So I would have 3 over 0, and that's undefined. So we can't have that. Okay, that's the bottom line here. So that's why they say, hey, I go and I pick this, b cannot equal this, and b cannot equal that. These are my restrictions. Okay? And that's what you're going to find out in this lesson. Whenever we want to know where something's undefined, okay, then we take a look at setting the bottom equal to 0 and solving. Because wherever it's equal to 0, those are our restrictions. If you have a whole number in the bottom, it's never going to equal 0. Okay? And we had a few other cases we just talked about. So be ready for class tomorrow, and this is where we're going to go and head into on this lesson.